Hello dear students, welcome you all. So in this lecture, I am going to discuss about the topic nuclear magnetic moment, right? So in this lecture, I will discuss in details what is nuclear magnetic dipole moment, right? And what are the reason for a nucleus having magnetic dipole moment. You can see here. Now the first and foremost question is that comes in the mind that what is magnetic moment? What is the physical significance of magnetic moment? So whether it is magnetic moment or it is electric moment, two type of moments are there. Both these moments tell us about the degree of either magnetization or degree of electrification of a material or a particle. If I talk about the magnetic moment, then magnetic moment will tell us, right, that up to what degree a material is magnetized. I mean, what is the strength of the magnetic field of that material. The same thing is applicable in case of electric moment. If I talk about the electric moment of a particle or a body, that will tell me that what is the degree of electrification of that body, or how much amount of electric field is contained in that body. So this is the meaning of magnetic moment and electric moment. Now here we are going to discuss about the nuclear magnetic moment. Nuclear means the magnetic moment present inside the atomic nucleus. Magnetic moment means magnetic field strength of the atomic nucleus. Now why the atomic nucleus is going to behave in this way or going to possess magnetic field and magnetic moment? We know very well that the atomic nucleus contains, this is the picture of atomic nucleus I have drawn, right? It contains protons, right? Let it is proton and it is a neutron. We know very well that atomic nucleus contains proton as well as neutrons. Forget about neutrons. If I talk about the protons, right, we know very well that proton is a positively charged particle that has charge plus E, right? And these protons inside the nucleus, they are not stationary, they are not stable, they are continuously, undergoing interactions with the neutrons and protons. We can say they are continuously moving inside the nucleus in random ways, right? I will not call that they are moving in circular paths or elliptical paths, because it is very a simplified thing to say, but in reality this is not going to happen. In fact, we can say that they are moving in closed paths. I mean, if I draw the lines here, let this is a proton, then this proton go this way, then they add this way, then finally this way, this way, this way, this way, this way, right, this way. So we can say that this proton or this neutron even, right, they are not moving along a straight line, but in fact they are moving along a these paths, which are curved paths, we can say. And when a body move in a curved path, right, then it possesses a angular momentum. We know very well when a body moves in a straight line, then it has a linear momentum. What when it moves along a non-linear path, right, its path is curved, bended, then it has a angular momentum. The same logic is going to be applied here for the proton, right? The proton is moving continuously inside the nucleus, and nucleus is, we know very well, it is having spherically symmetric shape. So we can say that the protons are moving inside the nucleus in a kind of closed path. We will not call them as either circles or elliptical paths. Once again I am repeating, but they are moving in closed paths. So obviously they have angular momentum, orbital angular momentum, we can say. Now we also know very well that the protons are charged particles, right? They have charge plus E, and we know very well then that when a charged particle move in a closed path, now it is equivalent to a flow of current in that path. You can see here, that this is the center of atomic nucleus, right? This is the center O, and let this is the path of a proton, right? I have taken this path as an elliptical path for simplification, but I am once again repeating that it is not always true that proton or neutron are moving inside the nucleus in elliptical or circular paths. We can't say, that generally, right? But for simplification, I am taking that this is the center of the nucleus and a proton of charge plus E, it is revolving in this way, right? Around this center, right? Now, when it is moving in this center, this movement of the proton inside the nucleus is equivalent to the flow of electric current I in this path, right? And we have learned in our 12th class that the small current loops, right? Small current loops behaves like a magnetic dipoles, right? How? We know very well that if I want to calculate the strength of magnetic strength or direction of the magnetic field in this loop, then I can find it by simply using right hand thumb rule, right? I can apply right hand thumb rule that will give me the direction of the magnetic field. So the direction of the magnetic field, if I'm taking these two halves of the loop, this is the upper half, this is the lower half. So you can see here in this lower half the direction of the current flow of current is this. So according to the right hand thumb rule, the magnetic field lines will be in this way, right? You can say. You can see here, because this will be the direction of the thumb, right? You can see here, this is the direction of the thumb. You can look at my thumb, and these fingers are pointing the direction of the magnetic field, and this is this thumb and this pen is pointing toward the direction of the flow of electric current, right? Similarly, if I go to the upper side, right, then this direction will get turned, right? So when I go to this side, right, in this case, now the direction you can see now this one. So now this one, when you will go in this way, now the direction of the flow of current is in this way. So this one, this will have this, right? So in this way, you can find the direction of the magnetic field that is arising because of the flow of electric current in this loop, and this current is arising because of the motion of a proton. So we have studied it in, as I told you, 12th class, that these small current loops, right, they behave exactly in the same way as a bar magnet. You can see here a pic, right? Now you can see here, as I told you, that this is the direction of the flow of current and this is the path of flow of a proton, movement of a proton, and obviously it is the direction of flow of current. So you can see here, right? Now as I told you that I can find out the direction of the magnetic field in this way and here in this way, right? So you can see in both the cases, right? You can see here and here, as I told you. So this is the exact representation of the field lines, right? Now you look at this loop. This is the small current loop and this is a bar magnet. So you can compare these two figures. They are exactly same. It means the small current loops, right, they are behaving exactly in the same way as a bar magnet. The direction of the magnetic field lines is nearly same. So that's why we are saying that the current loops, small current loops behave like a bar magnet, and obviously when they behave like a bar magnet, they have a magnetic dipole moment, right? Now magnetic dipole moment for current loops, we have calculated it and it comes out to be mu vector is equal to current flowing in the loop into area vector of the area of the loop. So this is the value for the magnetic dipole moment due to small current loop. So as I told you that the magnetic dipole moment, I told you in the beginning, it tells us about the two things. One is the degree of magnetization and the second is the direction of that magnetization, because it is a vector quantity, right? So now we are sure, we get clear that proton movement inside the nucleus produce magnetic dipole moment, but this magnetic dipole moment is called as a orbital magnetic dipole moment, right? Because we are considering the orbital motion of the proton around the center of the nucleus, right? So we call it as orbital magnetic dipole moment. right? So this is the formula for calculating it. So I can calculate it, right? So even I can start from here. Mu is equal to I into A. Let's take only magnitude I current into A area. Now current is charge plus E divided by time, right? So into area, that is pi r square. Let's take it as a circle. Then it is pi r square for convenience. This one. Then time, how much time it will take? It will take plus E divided by 2 pi r is the distance divided by velocity into pi r square. This is the magnetic dipole moment. After simplification, what value you will get? You will get that is plus E into velocity upon 2 pi r. This is the value of magnetic dipole moment, right? Now I can simplify it further. I am multiplying in the numerator and denominator with the m, mass of the proton. Then what it will become, right? It will become, I think I mistaken it. Let's calculate it. It will, I think, EV upon 2 pi r, it will get EVR by 2, because EV upon 2 pi r, it is this one only, EV upon 2 pi r. We have to multiply it with the pi r square. So EV upon 2 r into pi r square. So pi cancel, r cancel. So we get E B r divided by 2. Now this is the correct one. Sorry for it, I wrote it in a hurry. So this is EV r upon 2. This is the, now I am going to multiply it with the m in the numerator and the denominator. So mu is equal to E mb r divided by 2 m, mass of proton. I am writing it mass of proton. So what is mbr? Mbr is the angular momentum L, right? So L vector, or simply if I write it as L, then it is mbr. L vector is equal to r cross p. So it becomes now E into L divided by 2mp. This is the magnetic dipole moment value, right? Now this is the magnetic dipole moment, right? And if I write it in the vector form, right, mu vector is equal to E into L vector upon 2mp. It means the magnetic dipole moment of the proton, that is orbital magnetic dipole moment, it is directly proportional to L, and they are in the same direction, right? Whatever the direction of L, the direction depend upon the direction of the movement of the proton, right? Because L is equal to r cross p, right? We can say, so we can say r cross p is equal to m into b, right? So it depend upon the value of L. If they are moving in the counterclockwise direction, this one, right, this is the case, then the direction of L is along this side, and in this case the direction of mu is also along this side. So these both vectors are in the same direction, right? You can see here, because this term E upon 2mp, it is a constant. So mu directly proportional to L, and they are in these two vectors are in the same direction, but they have different magnitude, right? So this is magnetic dipole moment due to orbital motion of proton, right? Now let's come to the value of L. We know from the knowledge of quantum mechanics that L vector, or simply magnitude of L vector, we can write it as small l into h cut. Here small l is the orbital quantum number, right? Orbital quantum number, right? So if I put it here, then I will get mu is equal to E into L h cut upon 2mp. So I can write it further, E h cut upon 2mp into L, orbital angular momentum quantum number, right? This is different thing. This term is a constant, right? E h cut upon 2mp, right? So I am going downward. Mu is equal to E h cut upon 2mp into orbital quantum number L, right? Now as I am saying that this term is a constant. So you can see from here that the value of magnetic dipole moment, that is orbital magnetic dipole moment of proton, it depend on the value of L, right? This term is constant, and this term E h cut upon 2 time mass of proton, this is known as a nuclear Bohr magneton. Right? This is a unit for the measurement of magnetic dipole moments of the atomic nucleus. I have discussed already it in my previous lectures that we have two type of magnetons, Bohr magnetons. One is electronic Bohr magneton, that is E h cut upon 2me, and this is nuclear Bohr magneton. The difference is the mass of electron, mass of proton, and as the mass of electron is smaller as compared to the mass of proton, around 1836 times. So obviously this is a small quantity as compared to this. We can say that this term is greater than E h cut upon 2mp. So we can calculate the values even for both these constants. One is electronic Bohr magneton and the other is a nuclear Bohr magneton. So if we calculate the value of electronic Bohr magneton, we know very well it is 9.27 into 10 raised to power minus 24, either ampere meter square or joule per Tesla. You can use same dimensions are same. But now if I write it for this one, right, we know there is a difference of this one, much of mass between the mass of electron and mass of proton. So you can calculate, it will come out in this case, it will be 5.78 into 10 raised to power minus 5, not 10 raised to power minus 5, but 10 raised to power minus 27. I think it is, I wrote it wrongly. 5.04 into 10 raised to power minus 27 joule per Tesla. So this is the value. Now you can see the difference around 5 into 2 into 5 to the 10, so around 2 factor into minus 24 minus 27, right? It is around 10 raised to power 3. You can see, so you can say it is around 2000 difference. This term is around 2000 times smaller than this, so obviously due to this factor. So this is the difference between these two magnetons. Even we can write these values in terms of electron volt. So you can convert joule into electron volt. So right, if you convert it into electron volt, then you can do it. We know very well 1 electron volt is equal to 1.6 into 10 raised to power minus 19 joule. So you can do it. So you will get 5.78 into 10 raised to power minus 5 electron volt per Tesla, right? In place of joule, I took this one. Similarly, here you will get 3.14 into 10 raised to power minus 8 electron volt per Tesla. So sometimes, you can be asked to represent these values in electron volt per Tesla or joule per Tesla. So you can write them simply. You have to use the relation that 1 electron volt is equal to 1.6 into 10 raised to power minus 19 joule. So these are magnetic magnetons. One is nuclear Bohr magneton and other is electronic Bohr magneton. But I was actually saying that this is the value of orbital magnetic dipole moment of proton, right? So this was the expression for the orbital magnetic dipole moment of proton. So I can write it as mu is equal to L into mu n. Here mu n stands for nuclear magnetic nuclear Bohr magneton. It is written here. So I am using this word, here for representing this EH cut upon 2 MP, and L is orbital quantum number, right? So this is the value of a magnetic dipole moment of a proton due to orbital motion. Now this result that has been derived here, right, it is a classical result. When we use the quantum mechanics and we derive the quantum results, it is found that these results are quite similar to this one, but there was addition of a factor that is known as a correction factor or a Z factor, gyromagnetic ratio factor we call it as. So then we can write, if we use that factor in this way, mu is equal to Z L into L, right, into mu n. Here ZL is the Z factor orbital associated with the orbital motion, L is orbital quantum number, and mu n is the nuclear Bohr magneton, this one, right. So now it becomes the formula for calculating the orbital magnetic dipole moment of proton. The magnetic dipole moment of proton arising because of orbital motion, right. Now we know very well that I have explained in a demo lecture also that all the elementary particles do possess spin magnetic dipole moment. They also behave like teeny bar magnets. It means they have definitely spin magnetic dipole moment. Now I am also writing that spin magnetic dipole moment, let it is mu L. Now L stands for orbital magnetic dipole moment, then mu S, that becomes G S into spin quantum number S into nuclear Bohr magneton. Gs is the spin Z factor, right, spin correction factor. S is spin quantum number analogous to orbital quantum number, and mu n is the nuclear Bohr magneton. So this is the expression for a spin magnetic dipole moment in analog to this one. But once again I am recalling that in quantum mechanics we have seen that these elementary particles possess this magnetic dipole moment as their intrinsic property. They behave like tiny bar magnet, but it doesn't means they are spinning, right? They are rotating about their own axis, right? So now it becomes the orbital magnetic dipole moment, and it becomes the spin magnetic dipole moment of the proton. Now as far as this value of ZL is concerned, ZL is equal to 0, not 0, but it is 1 for I am writing its value proton, and its value is 0 for a neutron, right, because nucleus also contain neutrons, right. So if I, instead of proton here in this figure, I took neutron, we know neutron is a neutral particle, so its movement inside the nucleus or random motion inside the nucleus will not create electric current. I can't represent neutron in this way because it is a neutral particle. It means there will be no orbital magnetic dipole moment associated with the neutron, right. So I can say that mu L for neutron should be equal to 0. So that's why if ZL is equal to 0 and I put ZL is equal to 0 here for neutron, then I will get this is equal to 0, right. It means the orbital magnetic dipole moment of neutron is equal to 0, right. But for proton it is equal to 1. So for proton I will have mu L is equal to L into mu n, right. So this is the magnetic dipole moment, orbital magnetic dipole moment of proton, and this is for a neutron, right. Now I am coming to the second one, that is spin magnetic dipole moment. If I look at the spin magnetic dipole moment expression, it is this one. Then Gs, spin Z factor or spin correction factor, it is Gs is, if I write its value for proton, then its value is 5.585 and it is positive. But if I write it for neutron, then you will get surprised. It is minus 3.827. It means this is not equal to 0, right? Mu S is equal to Gs into S into mu n, right? This term is not zero for neutron. It is not equal to zero, but in fact it is negative, because for neutron Gs is equal to this value, right? And for proton it is this one. So you can see here, in case of proton, the value of Gs is positive. It means mu s, right, is positive. It is not negative. So we can say that the spin magnetic dipole moment and spin angular momentum, they are in the same direction. But here it is negative. It means when I will put the value of Gs, I will get something like this. Mu s is equal to negative, right? 3 point something into s into mu n. It means what? It means now that the spin magnetic dipole moment of neutron is negative. It is not equal to zero. Very, very important, right? And it is negative. Negative means the spin angular momentum and spin magnetic dipole moment, both these are oriented in a opposite direction. If this is the spin magnetic dipole moment vector and this is the spin angular momentum vector, they are oriented 180 degree opposite to each other, right? And the thing that it is not equal to zero, now it reveals that this elementary property, this property of elementary particle has nothing to do with the charge. It is an intrinsic property, and it also gives us a clue that these neutrons have some substructure, right? They are not fundamental particle, but they are made up of even some smaller particles that we know very well that they are quarks, right? And these quarks are in fact charged particles. So this measurement of the spin magnetic dipole moment of the neutron give us a reason, give us an idea that the neutron and proton have some substructure, right? They have some intrinsic properties, right? And their magnetic dipole moments are different, right? Neutron, even having no charge, possess spin magnetic dipole moment, right? So this is all about the magnetic dipole moments of nucleus, right, that I covered in this lecture. Now if we go to the total magnetic dipole moment, right, total magnetic dipole moment, then obviously it will be the magnetic dipole moment of proton, I'm writing it in vector form, plus magnetic dipole moment of neutron. So whatever neutron and protons are present inside the nucleus, we will add all these magnetic dipole moments, and then we will get the net magnetic dipole moment of the nucleus, right? Now as far as the magnetic dipole moment of proton is concerned, it consists of both mu L plus mu S, but as far as neutron is concerned, it consists only mu S, no mu L, right? So this is the way of calculating the total magnetic dipole moment of the atomic nucleus, right? So I think I have covered all the things that are important in this chapter, in this topic. So thank you very much